Hi viewers, welcome back to the channel. Today I have a question which was asked in GATE 2019. It's a very interesting problem because I usually don't see this kind of problems asking in GATE. So this was asked in 2019. It's a pretty important conceptual question. So as I usually say, use the first 2 minutes to read the problem on your own, then try to do it on your own, then come back and see rest of my video. Make sense? Now let's get started. Here we have a wire of circular cross section of diameter 1 mm. Especially when you are trying to solve problems from this kind of topics, let it be heat transfer, thermodynamics, solid mechanics, vibration, whatever it is, give give due importance to the units. So here we have a small wire which is of diameter 1 mm. It is bent into a circular arc of radius 1 meter. See, this is where paying attention to details is crucial. See, here you can see 1 mm and 1 meter. So you have to be very careful. You can't just simply take the numbers like it was of diameter 1 mm and then it was bent into a circular arc of radius 1 meter. It is not like that. The wire is only having a diameter of 1 mm while the circular arc is having a radius of 1 meter. This all may sound very pedantic or very silly to you, but let me tell you, these are all very important stuff, and these things really make a difference of 5 to 10 marks. That means a rank of say 1000, 2000, and all those stuff. So then they have given the Young's modulus of the corresponding wire. Then they are asking what is the maximum tensile stress. So the first question you should ask yourself whenever you're getting this kind of a question, you had a wire initially of like this and then it is bent into a circular arc, something like this. So the first question you should ask yourself is what kind of loading is involved in it? Because we come across different kinds of loading in solid mechanics or mechanics of materials. We will come across axial loading, then we will talk about torsional loading, then towards the end we talk about bending, then kind of mixed mode loading problems. So we come across all this kind of problems. So whenever you get a question, the first question you should ask yourself is what category does this particular problem fall into? It is clear it's a bending problem. Now the moment you hear about bending, the formula that comes to your mind is this very famous formula, uh, this one, sigma by y equal to m by I. This is, for most of them, this is the formula which comes into their mind. But apart from this, there is a formula that connects the stress to the curvature of the deflected shape of the beam. So this formula has to be given due respect, okay? Or this is also a very important formula. Make sense? Now we will look into the situation, what is given in the problem. So it is something like this, and just this is the wire which is having a diameter of, let's say, 1 mm, and then it is bent into a circular arc of radius 1 meter. Now let's take a small chunk of material, small chunk of wire which is somewhere here, then magnify it over here. That's what I have done. I have magnified it over here. So this is the initial configuration. This is the undeformed initial configuration. Okay, this is going through the center. I won't tell you the formula directly because this is something I don't like, so I won't do just the plug and chug. I will explain you the concepts. I will explain you how we arrive at these equations, then leave the rest of things to you. So that's how I operate. That's what I believe, because I want to make all these videos self-redundant. That means by the time you finish this video, you should be in a position to understand the concept rather than just solving a particular problem. You should be in a position to solve similar kind of problems. So this is the undeformed configuration. I have given some axis notations like this. Then it's very important, if you read the question very carefully, this kind of an application, this kind of a load application correspond to a uniform bending scenario. Uniform bending means there is no variation of bending moment across the span. Okay, it is pure bending moment. It's a uniform bending moment or pure bending moment. So the bending moment is not varying from section to section. So there are things like when you have a scenario like this, the deflected shape will be circular one. Make sense? So actually all these things are taken care when we are deriving this particular formula. So if you read a very good textbook you can understand that, but I'm just repeating those things. So here we have a pure bending scenario because the bending moment acting at each of these sections are same. So that's why the deflected shape, this is the undeflected shape. So this is the deflected shape. So the deflected shape assumes that of a circular arc with radius rho. That is what called the radius of curvature. So let's say I take a fiber. I take a fiber somewhere here. Okay, so this fiber is at a distance y from here. Then we know this particular fiber will be unstretched because this corresponds to the neutral axis. What will be the length of this fiber? Since this is unstretched, it is deformed, and undeformed lengths will be same. So its deformed length is rho times the radius times the inscribed angle will give you the arc distance. So this is the arc distance, this is the radius, and this is the inscribed angle. So the undeformed length will be the deformed length will be rho theta for this particular fiber. Okay, now once it is deformed, what happens to this fiber? Since this fiber is somewhere here, it gets shortened. So what is a reduction in its length? That can be easily found out from this diagram again, because this, if I define my y in this way, let me draw that for more clarity. So sorry, yeah, so this distance will be y. Make sense? So this radius of this particular arc will be rho minus y. So the initial length is rho theta, then the length reduces to rho minus y into theta. So change in length is this much. Simple maths. Now once a concept is laid out, rest of the things are fairly simple. Now you know what is the change in length for that particular fiber, and you know what was the original length of that fiber. Then you can easily evaluate the strain. Strain is minus y by rho. I arbitrarily took this fiber which is at a distance of y from this positive x-axis. So similarly I can take any fiber. So the outward, by common sense we can say that the outward fiber will undergo the maximum strain. Makes sense? Because this expression clearly lays out that or explains that as y increases, the strain increases. So what will be the maximum value of the strain when y will assume, because this rho is not going to change, because we are talking about an application where there are only pure bending moment. So the deflected shape will be that of a circle. For a circle, this radius of curvature is not going to change. Makes sense? So that rho is given, rho is 1 meter because it is bent to a circular shape of radius 1 meter. So what is a y max? This is very important. See, you are bending this wire. I am just magnifying. This is a wire which is having a diameter of 1 mm. Okay, this is having a diameter. So this is the bent configuration of a small portion of the wire. So this is having a diameter of 1 mm. So since the neutral axis will be passing through the middle, the maximum possible y max will be half of the diameter, that is 0.5 mm. Now rest of the things are simply plug and check. You can evaluate what is the maximum value of strain. Again, always pay attention for using consistent units. See, here I substituted r in mm and I again substituted rho also in mm. 1 meter corresponds to 10 to the power 3 mm. That's why this thing comes up. Now rest is simply applying Hooke's law, because they are not asking you what is the maximum strain, they are asking you what is the maximum stress. So by since the material properties are linear, or the material is linear elastic, you can simply multiply the maximum strain with the Young's modulus value. Again, use consistent units. I have used MPa here, then the stress will be in MPa. So the maximum stress will be acting when you bend it something like this. The maximum stress will be at these points. So these points will be under stress, under tension. So at those points will experience a maximum stress of 50 MPa. See, once again, go back to the question C. Again, pay attention to units here. There are this, you have to be very careful. The maximum tensile stress developed in the wire, you should plug the value 50. Had this been in GPA, you should not put 50. Even if you have done all this hard work, if you don't pay sufficient attention over here, you lose your marks. So if this had it been in GPA, then you have to write 50 into 10 to the power minus 3 GPA. So always pay attention to all these minute details, because that will ensure you your two valuable marks and better ranks. Thanks for watching.